Okay. Today we're gonna go over the linear perceptron, which was the first model for modeling the biological neuron formulated by McCulloch and Pitts in 1943. And here now there is a sketch of the anatomy of a neuron, and here now you can see this part here, which is called the dendrites, which that comes from the Greek, so which means a tree. Indeed, these are all, they're all shaped like a tree, and that's where now here they feel they are sensors that feel all the inputs from the signals from the surrounding environment, and so they collect all the signals that get into this area, which is called soma, which is the nucleus of the neuron, where eventually, will make a decision if activate a potential to go through the axon and through the terminals, and through the axon terminals, the activated potential basically can transmit information to other neurons through their own dendrites. And so here you can see that here we have this part here is basically an input. Then here we have a central system that elaborates this input. And then through the axon, here there is an activation process which decide, if transmit through synapses all the information through the axon terminals, leading to an output. And then what happens is that this output will become the input of other neurons and then forming a so-called neuronal network. And so the mathematical model of a perceptron can be taught in the following way. So here we have a nucleus, and here they receive inputs. Let's assume that these inputs are given with n parameters. So here we can define an input as a vector given by the list of x1, x2, xn. And inside here, there will be is the black box of the neuron, or the so-called perceptron, which compute the dot product of the input with a weight vector and a bias. So W is the weight vector that has the same dimensions as the neuron, as the input. This is the input. This is the weight vector. And then B is the bias. And then, this is basically, modeling the soma. And then what happened here, it will undergo through an activation function. And then the output Y will be, for simplicity here, will be the sign. I'm going to explain now what is this. W dotted x plus b. So, and this is the, the model of the perceptron. And I'm going to explain now in all the details what all this quantity means. So first of all, the input is binary. It means it can be just plus or minus 1. Each of the components of this vector are binary. And the output, we're also going to assume that it is binary. Can also be plus and minus 1. Okay? And what we're gonna do today now is try to understand, what are the properties of this perceptron, and how can we use it, to model. So let's start it again and do a nice formulation here of the perceptron. So here we have the input. And for simplicity, let's assume that we only have two inputs, okay? X1 and X2. N equal 2, okay? So the vector X input is given by a list of two numbers. And all the components Xj, they are binary. They can only be plus 1 or minus 1. And then inside here, we do the dot product with a weight matrix, a weight vector, and a bias. The weight vector is given by two components, W1 and W2. And then we have B, that is the bias. These are the weights. And then what happened here, based on this value here, the output Y will depend upon the sign of this quantity here, W dotted X plus B. And this function here, it is simply, let's call it this quantity S. This is 1 and minus 1. So the sign of S is equal to plus 1 if S is greater than 0, and minus 1 if S is less than 0. Okay? So this is basically the activation function. Which, I mean, it can also be replaced in general by another type of activation function, call it sigmoids. And this is more a more smooth behavior of the activation function, which is called sigmoid function. And there are many functions, even hyperbolic tangent, tangent, the regular tangent of S has this kind of behavior, and so on. And but we're gonna focus just on we're gonna use the sine function. And so the linear perceptron, it is basically a first model which allow to basically do binary classifications. And we're gonna use it to model a Boolean gate. In particular, no, we're gonna focus on doing the OR gate. And we want to find what are find the weights and the bias of the perceptron such that the perceptron models the OR gate. And we're gonna see how to do that. And but first of all, let's try first to understand what is the if there is a geometric interpretation of how the perceptron operates and why it is a good model for a binary classification. And in order to do that, we have seen that actually, I'm going to start a new page. So this is the model. I'm just going to focus on two inputs. Inside here, we do the dot product. And then through the activation function, the output will be just another binary scalar, omega x plus b. First of all, let me remind you what is the dot or scalar product between two vectors. W dot x geometrically is equal to the length of the vector W multiply the length of the vector x multiply the angle between them. So indeed, the dot product is useful if I have these two vectors. I can compute basically, if I know their length, I can compute the angle between them. Of course, this is a geometric definition of the dot product. This is geometric. So I just need to be able to draw vectors, which are just a length and a direction, and then measure the angle between them. If the vectors are represented in components, one can show that W dot x is equal to Wx1 plus Wx2, the element-wise multiplication of the components of each vector, which we can also express it with the notation sum from j equal 1 to 2 of wj xj. Okay, so and that's the one that we're going to use. And but first of all, let's understand what this perceptron is doing. So, and to do that, let's consider the input space, which in our case, it is the plane R2. We have two components. And as you can see, the output, remember that the output y can only be plus and minus 1. And in particular, y is equal to plus 1 if w dot x plus b is greater than 0 is equal to minus 1 if we have the other negative sign. Okay? So you can see that this quantity is very important. Whatever is computed inside the soma of the neuron will determine, the sign of this quantity here will determine the output. And also remember that x1 and x2 are binaries, quantities. So let's understand what is this quantity here, wx plus b equal to 0. This is where this is called the decision boundary. And what is that? If we apply the dot product formula, we get this expression here, which in the plane, in the input space, we can also call it the input plane, represent a line. And we can easily, how to plot this line? I mean, we can express the x2 equal minus b divided the w2 minus w1 over w2 times x1. So this will be easy to plot the lines. And so, for example, depending upon the values of w1, w2, and b, the perceptron parameters, for example, I mean, when x1 is equal to 0, we know that the line will pass through the point b over w2. And then we also know that this is the slope. And so now we can basically compute the tangent of this angle is the slope, and with a sign, of course. And so this is basically the decision boundary. And what happened that all the inputs that are above this line will give me an output of plus 1. All the inputs below this line will give me an output minus 1. So you can see that here we have the plane has been divided into regions. The region which gives me a positive, a plus 1 output, and the region that gives me a negative, a minus 1 output. So it is clear that what the perceptron is able to do is to do a binary classification of our inputs by simply finding a special line. Okay? And so now we're going to apply this concept. We're going to try to find what are the weights and parameters so that this perceptron can model an OR gate. Okay?